Hello students, this is Professor Chalai, and in this video we're going over some of the things that you'll need to know for this week's lab on weak acid equilibrium. The whole purpose of this lab is to find a Ka of this weak acid, acetic acid, which is otherwise known as vinegar, right? So we'll have our H plus and our acetate ion, and our whole aim is to find the Ka of this acid. And we're going to do this in two ways, in two parts. For part A, you're going to find the Ka by varying the concentrations of this acid, varying concentrations. And for part B, you're going to find the Ka of this acid by making buffers. And so I'm going to walk you through how each of these work, how we can do each of these experiments in theory to find a Ka of some acid. Now, we're not going to do acetic acid in my example here, but I'm just going to use some generic acid. Let's say some generic weak acid HA, right? So this is what we're going to work with, some generic acid. And we want to find a Ka for this generic acid. Okay, so let's look at how we're going to do this in part A of the experiment, where we just vary the concentrations of this acid. So let's say we start with some stock bottle concentration of 0.100 molar. This is my stock bottle concentration of that acid. Well, I can vary this by making dilutions, right? Like I can make a 1 in 10 dilution, which means I'll take, for example, 10 mils of this, add it to a 100 milliliter volumetric flask, and fill the rest up with water, and that's a 1 in 10 dilution. If I want to make a 1 in 100 dilution, I don't need to take 1 milliliter and dilute it to 100 milliliter. I could also just take 10 milliliters of this 1 in 10 dilution and dilute that up to 100 milliliters. So that's what we're going to do. We're going to take a stock concentration of the acid and dilute it 1 in 10, and then 1 in 100, and 1 in 1,000, and then find a pH of each of these. So let's just say, for the sake of our argument here, we find a pH of this one to be 3.46, the pH of this diluted one to be 3.96, and the pH for this 1 in 100 dilution to be 4.46. How can we use that information to find the Ka of this acid? And just as an FYI, if this stock concentration was 0.100, if we made a 1 in 10 dilution, this concentration would be 0.0100 molar, and a 1 in 100 dilution would be 0.00100 molar. Okay, how do we use the pH of these diluted solutions to find the Ka of the acid? Okay, let's think about an ice table for this acid. Okay. There we go. Ice table. All right, let's work with this one here, our stock solution, where it was 0.100 molars, and we found a pH, and the pH was 3.46. Well, we can have this, subtract x plus x, right? And here it's 0.100 minus x. This is x, this is x. We can't assume that x is small because we don't know what the Ka is, right? So we can't assume x is small. But we do know that the pH, this pH right here, is related to this H plus ion at concentration. In fact, the H plus ion at equilibrium is 10 to the negative pH. So that H plus ion concentration should be in this calculation right here, 10 to the power of negative 3.46. I get an H plus concentration of 3.5 by 10 to the minus 4 molars, which is basically x. Now, in this case, x is small enough that it doesn't really affect the concentration, but I'm going to recalculate all of it. 0.100 minus that value of x gives me 0. It doesn't change this number at all. X here is 3.5 by 10 to the minus 4, as is this x. So we know that our Ka is going to be equal to their H plus concentration at equilibrium, your conjugate base ion concentration at equilibrium, and your HA concentration at equilibrium. So in this case, it will be x times x which x is just this number squared divided by 0.100. That comes out to be, sorry, a Ka of 1.2 by 10 to the minus 6. And you're going to repeat this for each of the various dilutions that you make. You'll find a pH, plug it back into this table, and use that information to find the Ka of your acid. Okay, for part B of this experiment, we're going to make buffers and find the pH of the buffers. Now, remember, a buffer needs an acid and the conjugate base of that acid. In the case of the lab, the conjugate base was the acetate ion. And of course, you can't just add a single ion to a solution. So we're going to usually add this in the form of sodium acetate, either written this way or this way. But sodium acetate is the ion that contributes our conjugate base. But let's think about our ice table in that situation where we have a buffer. We have a starting concentration of both HA, the acid, and A minus. So we have a starting concentration here, and we have a starting concentration here. This starting concentration we will get from the stock solution. I don't think we're going to dilute that. This starting concentration of the conjugate base, we're going to add solid salt. And the great thing about adding a solid is the total volume doesn't change, so we don't have to like recalculate our concentrations, but it means that we'll have to figure out the mass of the salt in grams and then calculate the moles of the salt and then divide that by the total volume to give us the molarity, right? But once we have the molarity from the grams to moles and then molarity, we have our starting concentration of conjugate base. And then the rest of it, let's say we'll lose X amount of this plus X amount of that, right? So we'll have whatever this starting concentration is, let's use purple, minus X. And then we'll have whatever starting concentration of conjugate base or salt that we have plus X. So as long as we find out what X is, we have all of our equilibrium calculations. We can find out the Ka for this acid. But remember, when we create a buffer solution, we can also calculate the pH using the Henderson-Hasselbalch equation, right? Log of A minus concentration over HA concentration. And, you know, we know this is a weak acid, so really we can also just assume that these the starting concentration of acid is the same as the equilibrium concentration, and the starting concentration of conjugate base is the same as equilibrium concentration. So we can use initial concentrations there. With that, the pKa will be the pH minus the log of these two concentrations, which we already know, right? And we also know the pH because that's what we're going to measure. So we can figure out the pKa from creating this buffer. And then the Ka is just 10 to the negative pKa. So in part B, creating this buffer, this is how we're going to find the Ka of our acid. In part A, this is how we're going to find our Ka of our acid. And that's the gist of the lab. Some things to note here, we'll be using a pH probe. So you need to calibrate your pH probe. And to do that, you'll need to feed it buffer solutions where we exactly know the pH of those solutions. And since we're going to be dealing with a weak acid, we want to calibrate it to, accurately find a pH of weak acid. So we'll have two buffer solutions, one at 4.00 pH and one at 7.00 pH to calibrate with. The other thing that you want to pay attention to is you need to make sure all of your glassware are clean with deionized water before you start running any experiment. And then for cleanup, the acid that we're going to be working with in lab is just vinegar, so you can just wash down the sink and then clean everything with distilled deionized water. That's it. That's all you need to know for this week's lab. I will see you in class.